Hey folks, it's Dave Swanson. It's the 9th of August 2026, and I want to make a fairly short video here. I wanted to show you this little widget that I created with the help of AI using the data sets that I've gathered. And what we're looking at here is we're looking at a time animated graph. The blue oscillatory lines are actually the moon distance from Earth on given dates. I've taken the data and found the moon phase, the percent illumination, the moon distance, and something I'm calling the gravity tidal strain. So the blue is the moon location relative to Earth. So on the bottom, closer to Earth, further from Earth. So at the bottom, it's roughly 346,000 kilometers from Earth. And then once again, the red dots in this case are the Kilauea Volcano. I also put in an eruption from Mount St. Helens and other volcanoes. We have a time rate, so I can make it go faster. You can make it go slower if you want. We can pause and skip one day at a time so we can see the daily cycles go back or forth one day. We can restart, and we can just jump to eruptions that are next in line. So like on this one was February 14th, 1902. The moon was first quarter. Illumination was 37%, and this gravity tidal strain was 1.08. So why did I do this? What does it show? So let me just give you a quick background, and then we'll come back to this. Willsey did a video a couple weeks ago where he said, can the moon trigger volcanoes? So he tested Kilauea's last 51 eruptions. And basically what he tested was from January of 2025 until current, which is pretty much one eruptive cycle with a bunch of different eruptions in it. And he ran some tests. He got what to me looks like a bimodal or bimodal, I think is how it's explained distribution. It's an interesting video. I'd watch it. I really like watching Sean. I like him when he gets out in the field and makes those drawings. He kind of inspired me to look at some different things. Very good video. So I realized that these moon phases, they might have equal angular distances between them, but the time that it takes for the moon to traverse these distances is different. So kind of a one-to-one type of analysis isn't necessary because the moon is actually going slower at apogee and perigee relative to the rest of the time. So I think that's pretty interesting. So he kind of inspired me to look at something a little bit different. So I went to the Smithsonian global volcanism program, and I looked up Kilauea and I looked up its eruptive histories, and I went back. So pretty much what Sean is looking at is this episode here where we're still more or less, I think, in the same episode. It says continuing. So he's looked at basically eruptions in this time frame in this one section. What I did was I went back to about 1902. Where's 1902? Somewhere down here. And prior to that, it was plus or minus 5 days, or they didn't really know. So I tried to stick in the modern world. And what I would do is I'd come in, say this one here, September 13th to October 1st. You can see it's a time range. I didn't worry about the time range. When you drill down on these, you can see that on September 13th, fissure started and there was lava. So that's the day I looked at, not all the extra days where there were lava fountains and other things going on, because to me, the start date of the eruption of this series is what's important. It's been pressurized, it's been opened, so there may be things going on, but to me the most significant is the initiation of that. And so I took 60 data points from this, and I used let's see here, Then I went to the NASA Jet Propulsion Horizons website. It'll print out really accurate data for a bunch of things. So I chose the moon. I chose the observer location being Kona, Hawaii. I specified from the 1st of January 1902 to the 31st of December 2024, take 1 day steps. And what this table put out includes all these columns of data. So constellation ID, or orbital plane angle, defective illumination, visual magnification, surface brightness, range. This has the distance. It has all kinds of stuff. This, I'm not going to show it to you, but the data that came out of this is about 44,000 rows and like 50 something columns. It's a huge data set, but it includes the moon's distance very accurately and some other things which will allow me to calculate the phase of the moon. There's not one category that says, oh, it's waxing crescent or anything like that. It has to be tested based on the illumination fraction and some other things. So I gathered all this data and I decided to perform a similar test to what Sean did, but of course this is a lot less granular. What Sean did was very granular. He didn't really find any, any relation to the phase of the moon to an eruption. So I put together my list, and let me see if I can find that for you here. So I created this master list starting with the first eruption in February 1902, and I just filled the data. I got the moon distance from that 45,000 data point series. I did some statistics and calculated the z-value and the absolute of the z. Not going to talk about that. And then this tidal force approximation, which is basically a normalized third power type of analysis, which allows kind of a general view into the let's say the tidal force that the moon exerts on the Earth. And basically these moon distances on the main chart, like I said, there's 120 days of moon distance that I calculated. So this tidal force approximation takes the moon distance on the day of an eruption, divides it by the average of that huge list, and takes the cubed root of that and then divides that by 1. So basically when this distance is exactly the average of that larger list, we will get a 1. When the moon is further away from the Earth, there's less tidal stress. The number goes below 1. When the moon is closer, it gets greater than 1. And, pardon me, so I created this list of all the eruptions and the distances. And right now they're in chronological order, but what I did was I can sort them by moon phase. And we're going to see that we don't have an equal distribution. We have more in some other categories than others. And once I created this list, this is what gave me the push to do that other first time animated graph that I showed you. So when we do this analysis, what we get when we sum everything up for these different phases is the following. Shown graphically for these 60 eruptions from 1902 to 1924, we get this. So what I've noticed is on a new moon or full moon, there were fewer eruptions from the Kilauea system. When the moon was 90 degrees opposed to that configuration, we also got fewer. We got 5 on the first quarter and 2 on the third. When we look at the intermediaries of these, we see those are where the significant eruptions are. So coming into the new moon and coming out of the full moon, there were definitely more eruptions in these Kilauea systems, and more or less kind of the same thing coming in and leaving the full moon, although 7's really not much greater than 5. But so these are the 60 eruptions when they initiated, and like I said, some of them lasted weeks, but this was the initiation for the onset of these eruptions for 120 years. So there's definitely some statistical hump here. So looked at statistically, I binned these up and I did a chi-squared statistical analysis, and we got a pretty low number, 0.00031, which that number kind of signifies that this is not a standard distribution, but it really kind of is, because what we're seeing, without going into much detail, is bimodal distribution. So here's how they look on a chart. They're just more or less sorted. They're not really in any kind of order. And here's that chart again. So the tidal force gradient is kind of interesting, even though, like I said, this is just a cubic approximation based on the normalization around 1. But you read these as percentages. So at 100%, this is the average. This is not a location, but this represents the average tidal strain when the moon is at its average location from Earth. And you can just see, as we go up to 105% of the strain, 110, 115, we start to see more eruptions. So as we get more strain, this means that the moon is closer to the Earth. When the strain deviates from the average to go lower, that means that we're further away from Earth. And it's an interesting distribution, which actually looks like this, where this 38,500, this is the average distance the moon is from the Earth throughout 120 years of data. That's the average. And you see we have a little peak at that point, and then we have a drop and another peak and a drop and another peak. So this is indicating data that is distributed on either side of a central point bimodal distribution. I believe there's all the point, and so this is the distance from the Earth, and this is the counts. So at 365,000, we had 7 fell into that category from that previous graph, and vice versa. So we basically have, I believe, when you count up these data points, we have one less data point on this whole side from here to here than we do here. So if you count it up, 2 plus 14 plus 7 plus 4, and you did that math. So the data is very equally distributed. We have a hump in the middle, but what this is saying, and of course these are eruptions, so what this is saying is, yeah, we have eruptions right around the moon's average point from the Earth. We do have some eruptions on either side of that point, either closer to Earth or further, but there's fewer. But then as we get further from Earth, we get more eruptions, and as we get closer, as the moon gets closer to Earth, we get more eruptions. So this is what this data is saying, and there's definitely a little bit of skew to it. But so let's get back to the chart. So, we kind of want to explain what's going on here. The full moon isn't any of these locations, any of these phases, is not necessarily at a fixed distance from the Earth. So there are times where the full moon is closer to Earth, and there are times when the full moon is further from Earth. And the same goes for all of those. And that's pretty much why I wanted to go with, let me pull it up, making this chart, because we can get a really good visualization. So before I go too much further, I want to show you a couple things here first. Let's just look at 2 years, okay? And I'm going to put on these upper and lower. Well, let's go back to 5 years. So I've marked the lower bounds and the upper bounds. Obviously, the lower is closer to Earth. We're further away here at these distances. So we can see the top has a nice kind of um, little seesaw pattern. The bottom which is closer to the Earth, has a much more varied type of pattern. But what we're going to see where I've marked these eruptions are marked. I'm going to go into 15 days. These eruptions are marked along the moon line because that's the distance that this eruption was from the Earth on that day. So let's go to looking at this first eruption, which happened February 14th, 1902. The moon was first quarter. This was the distance. The tidal strain was 1.08. So it's 108% strength that it would have at the average. And so I've done that with all of these, but what's interesting about the way this data is we'll see again and again um, something that's pretty regular. And what we're going to see is, you notice how we have these periods where the moon in its orbit is closer than during other periods and further in its orbit. And then this orbit tightens up so that the distance shrinks. So the moon is actually, even though this is perigee, it's still further from the Earth than perigee here. And the apogee here, farthest from Earth, is actually further than apogee here. And so we're going to see, and so this is a very repeatable thing that goes on and on and on. And what we're going to see is a couple things. Number one, we're going to see a lot of eruptions of these 60. We're going to go through them all pretty quick, that happen right about perigee, and a lot that happen right about apogee, wherever they're at. Then we're going to see a lot that fall in this more tighter range where the moon is in a tighter orbit around the Earth as far as the difference between perigee and apogee. Okay, so we're going to see this time and time again, and it's really interesting, and somehow that relates to the data showing the moon phase. I'm convinced of it. I haven't figured that out yet. But so let's go to this first one. You'll have to kind of keep your eyes down here. So the first one is on February 1902, first quarter. We went through this one. The next eruption, once again, very near perigee. And I'm going to put it on, let's back out to 90 days. Okay, so you can see here, if I click on the map, it puts my cursor there. And if I go one day at a time, you can see 1 day increments in this. So if we go on this, so this is that June 3rd, 1902, waning crescent. We can see how many days until perigee. 2 days. So it's 2 days away. The eruption happened 2 days from when the moon was going to be at its closest to the Earth. So I'm going to put on 5 years, and we're going to kind of just go through next eruption. This eruption's at apogee, near perigee again. Near apogee, and in this small range here of the tightened flow. Here we are, the eruption happened at perigee. Perigee, apogee, pretty close to perigee, pretty close to apogee, almost apogee, almost apogee, almost perigee, apogee, and this is the end of the list, almost perigee, kind of mid-range, apogee. And so, when we go through this, we see, um, and this is kind of indicated in the tidal strain because they're kind of related, that most of these eruptions in this 60-year period are happening when the moon is either in this phase where it's has less deviation in its orbit. It's only really going from 360,000 to 390,000 miles in the distance, where here we're, maybe about 10. In fact, I did the calculation from about this point here to here is about 10,000 kilometers, and from here to here is about 20,000 kilometers difference. So there's some significant things. So I'm going to turn off this moon distance, and we're going to go to the full data set. So I just kind of wanted to also show for Kilauea in this 120-year period, starting at 1902, we had eruptions, and this is probably part of a larger series of activity, but it basically goes to 1906. So we got a 4-year period of eruptions. Then from like 1906-7 to 1917, we had a lull in here where, was that 10 years or so? Then we had activity from 1917 to roughly 1934, so 17, 20 years. Then we had a lull from 35 to 52, so almost 20 years. Then from 52 to 84, another 30 years of activity. And then we have this big dead spot from about 83 to 2020. So that's 37 years or so where there's no activity. And so then I also put in the Mount St. Helens eruption, Nova Rupta, Mount Pinatubo, Hunga Tunga, Hunga Apai, Santa Maria. Oops, I didn't click that one. And these are the perigee and apogee envelopes. Those were the lines that I showed, that I put on there. So when you just look at, so these are the high points of the orbit, these are the close points. So when you look at that, we'll do 5 years. We're going to see that there is some action happening in mid-orbit, but a lot of these fall right at the extremes. Let's reset this. And pretty close to the extremes of perigee and apogee, and Nova Rupta. And then we'll see once again in this area where the orbit is compressed, we see that again and again. So in the lower area at perigee, here in the lower area at apogee, near perigee, mid-range, kind of further away, right at perigee, apogee, perigee, mid-range, apogee, perigee, near apogee, apogee, kind of mid-range. That was just like a couple days. That one is 1, 2, 3, 4, 5, like 5 days away from each other. Here's another one that's perigee, right near perigee, kind of mid-range, perigee, mid-range, apogee. In this lower section again, in here again, in this lower section where it tightens up, we had 4 in this period from August 68 to June 69. Another mid-range near apogee, perigee, 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 mid-range, perigee, perigee, mid-range, but still in this lower, tighter constricted area, apogee, near perigee, apogee, and we're getting here to the end, starting in like 2020. So this eruption is not quite apogee, but it's in this constricted section as we're coming out of it, near apogee. Hunga Tunga was near apogee, once again in this lower section. The next eruption was right near apogee in this compressed section. The next eruption was, right, almost right at perigee, near apogee. So there seems to definitely be a correspondence to times when the moon is closer to the Earth, having volcanic episodes, and when it's further from the Earth. And we can, play with the different settings on this. If anybody wants this, this is an HTML file with all the data loaded in it. I plan on making this pretty extensive in the future to have multiple eruptions. Kilauea is the only one that has multiple eruptions. All the rest are just individual main events, but these are big events when they happened. And maybe do a few other changes. But let me just kind of go back, and I'm going to put this on full data set, and we're going to put the moon's distance. And so looking at it in a 120-year period, you can see now the moon is, the average moon distance is right about where my cursor is across here. I didn't put that in, but you can see we have a lot that are grouped in the upper areas and a lot that are grouped in the lower areas. And even when we zoom into some of these areas, let's look at 6 months, or let's look at 5 years around this point. Even when we zoom in, it's because of the scale of the graph and all that, you can't really see how close these are to these kind of these cardinal points. So I put a little spreadsheet together, which is similar to these other chart that I showed you. But this is the average moon distance. So the moon with Earth being the closest to Earth, furthest. And these are the 60 points. It ends here at 60. So this is the average distance is actually 385 right there. Sorry, I moved that. So you can see, we have some occurrences on the average, but as we get further away from the average, which is closer to Earth here, we get a group of variables and we get a group of variables. So we're not seeing this distribution through this data evenly, and so that's actually pretty tightly. I did all the math. I won't bore you with it, but the variance is so small, and that it's almost a totally symmetrical kind of distribution based on the median being that 385,000. So once again, we can just go back to this chart, which I think it's pretty cool because it just has like a lot of features. You can really see where things are lying on here. You can really zoom in to even 2 days. It's just a line. It's like nothing. But we can do 30 days, so that's a month. We basically start at 402,000, come to 366, go back up. But let's put on 6 months, and let's get rid of these things. and put on 5 days, and it's kind of fun to watch. You can really deep dive. Oh, that's what I was wanting to show you. Is let's look here on this one, and I'm going to even go in further to 30 days. And when we click on this, like I say, we can go back to perigee. 1, 2, 3, 4 days. So, this location is 4 days. When you look at this perigee to apogee, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. So there's roughly, in this instance, roughly 13 days where the moon is its closest and furthest from the Earth. And if we look at this, let's look at it on 2 years. So if we look in these small sections here, it's usually here we go. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. It's 12 days from perigee to apogee. If we look over here, let's make sure we're centered. Okay, we're 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, roughly 14 days. So the one thing is because the moon is closer and further in these sections, it's traveling much faster for the same amount of time, and the moon is actually traveling slower in these sections. But anyway, that's what I wanted to show. I'm running some math on this, but there is a definite, we're seeing a definite type of behavior where when the moon is closest and furthest, not maybe 100% on the day, but in those general areas of the cycle, that's when these eruptions have been occurring across a wide variety of time frames. And so, I don't really know what that means, because there's no way, I think, to predict anything. So I can't predict a volcano eruption date, but I would say that if we knew a volcanic system, say Kilauea, was pressurizing, if there was some going on and we were heading into these sections of the year, where the moon gets closest and furthest is basically like December to June, and then from June to December, it's this lower sections generally. So if there was a volcano pressurizing, or we were seeing some signs and we were coming into this tighter bounds, I would look for possible activity around perigee and apogee. And but there, I still don't really have the numbers. I know I'm not the only guy on the planet that's ever played with this. I just happen to be able to use a huge data set and AI to make this really nice animated time series type of graph. I'm going to put it on 6 months. So every 2 seconds is a year. So it's really pretty interesting. This gravity tidal strain is the real indicator, because the eruptions do actually occur when the tidal strain is mostly greater than 105% of average or less than 95% of average. And we see a lot less activity in the bulk of the center. We see some in the bulk of the center between these two extremes, like right here, many years apart. But we see mostly at perigee and apogee. And along with the other data for these 50 eruptions, which includes this. So in those 50 eruptions, we definitely see some favoritism, and it seems to be geometric. In other words, inline, moon here, or sun here, in line with the moon, 90 degrees opposed, less activity. When we have some kind of shearing action, is what I'm going to call it, because the force is now a mix between the Earth, Moon, and Sun is now mixed with a vector. We see more at these star points, I'm kind of calling them. Um, so I think there's definitely, something that, maybe can be flushed out in the future by somebody. What I want to do and what I'm going to do just for fun is to start sucking in a bunch of different volcanoes and their eruption dates all over the planet. And of course, this is a little hobby that I do outside of my work, so I don't know how long, but I have the fundamental basic uh, infrastructure together already. And, I think that it'd be kind of interesting to really get some good records like we have for Kilauea and see if there's any correspondence to these particular moon phases. See if they happen right at these times where the moon is almost the furthest from Earth in the cycle and almost the closest to the Earth in the cycle, um, as well as what the moon phase is. And, I think that's just kind of a nerdy thing to do. Here's Pinatubo right here, coming by pretty darn close to perigee. And I don't know. These are long, 14-day one-way cycles, 28-day cycles. Uh, there's probably actual math that can be calculated. I didn't have eruption times, so all my data is set for noon on UTC for these dates. But there's probably some math that can be done with the actual location of the moon, sun, and Earth, and to kind of triangulate to see if there's any kind of things like that. But what started out is just kind of looking at what Sean Willsey was doing and what he found, and just trying to more or less try to duplicate it and see if we can, if I get the same results. This is what I came up with. If anybody wants the this HTML uh, uh, animated graph, I can let me know, and I'll put a link down there. I don't know if anybody's ever going to really want it or not. So anyway, Dave Swanson, thank you for your time. Take care. Bye bye.